All right. There we go. Okay, let's get started. Let me get the sign-in sheet passed around. So a little bit of housekeeping. You all know that homework 4 is due today. Homework 5, that title's wrong. That's supposed to be stresses and beams. It's going to bug me. I'm going to go ahead and fix that now. All right. Stresses and beams, that's due Thursday on the 25th. I don't have it on the slide, but I guess I should go ahead and mention this, that on Thursday, October 25th, you all are turning in homework 5, but homework 5 is on the exam, okay? So I'm giving you the solution that day, okay? So I guess, you know, on homework 5, I guess the point to mention is that it's going to be tough for me to accept late homework if I'm giving you the solution the day you turn in the assignment. So make sure you get homework 5 turned in on time. But yeah, I will give you the solution for that. You all are turning in homework 4 today. My goal is to get that graded and back to you by Tuesday. If I don't get it back by Tuesday, the solution will be given to you Tuesday. So one way or another, you will get a feedback on homework 4, and homework 5, you'll get the solution the following Thursday. Sound good? Okay. So today, I want to try and knock out as much bending stress stuff as I can, or beam stuff as I can, I should say. We're going to finish the composite bending example today. We're going to finish that today, and then we're going to get into transverse shear stress. Transverse shear stress is a pretty straightforward process. It's not that difficult. The derivation is a little, I don't want to say intense, but it's interesting to say the least. But we'll do that. We'll probably do the derivation today. We should get through some of the example, and if shear stresses bleed into next Tuesday a little bit, that's no big deal. But just so you're aware, beam deflection will not be on the second exam, okay? The second exam ends at transverse shear stress, so just keep that in mind. Okay, so let me go ahead and just get back into it. So this is the problem that we were working on last time, okay? So here's the problem we were looking at last time. We had a wooden beam that is essentially a composite structure because it's a wooden beam and it has a steel plate on the top and bottom. And what we're trying to determine is how much moment can be resisted by the wooden beam and by the composite section, okay? Now, when we did the problem in class, we started the problem last time, and we didn't quite finish it, but what we did last time is we said, let's look at just the wooden beam by itself. And so if you look at the wooden beam by itself, you have a beam that's 10 inches wide, 12 inches tall. It has an allowable bending stress, or allowable normal stress of 1,000 psi. What's its maximum moment? Well, if you know the moment of inertia, BH cubed over 12, and you know your stress formula, bending stress formula, sigma equals mc over I, rearranged to solve for m, you know that c is half your height, plug and chug, and you get a maximum moment of 20 foot kips. Okay? Now that's the maximum moment without the steel plates attached. Now let's affix the steel plates and let's see how does that improve our capacity. You know, spoiler alert, it will improve our capacity a significant amount, but let's see specifically how that's done. Okay? Now, if you recall, one of the things we derived last time was the concept of the transform section. The idea that if you have a beam that is made of, let's say, 2 materials, we need to transform it into a beam of 1 material. And the same thing would hold true if you had a beam made of 15 different materials. Your bending stress theory only applies to expressions of beams that are comprised of 1 material, so we have to transform them. So let's look at the composite beam. Okay, so here's the composite beam. Now, in order to address this composite beam, I'm going to write a couple of things down. Okay, so sigma allowable for the wood is 1,000 psi, and sigma allowable for the steel is, let's see, it was 18,000 psi. Okay? When you're dealing with a composite beam, you get additional strength, but you actually need to check both materials because you have to determine which one governs the capacity. And we'll talk about what governs means here in a second. All right? Now, there's a couple other material parameters I need to look up. I have the E for the wood and the E for the steel. Now, for this problem, the wood has an E value of 2,000 KSI, and this is 30,000 KSI. Okay? Everybody okay with that? Now, whenever you are dealing with a composite structure, you need to transform it into a beam of a single material, and you do that through the use of a modular ratio. Okay, so the first thing that we need to compute is the modular ratio, and that's this quantity N. Okay, so I'll put modular ratio is N, and typically when we compute N, we take the E for the stronger material and divide it by the E for the weaker material. So I'll write that sort of in general as E strong over E weak. Or another way you can think about it is just the larger E value divided by the smaller E value. And the reason for that is we want our N values to be larger than 1. So we have 30,000 divided by 2,000. And what does that come out to be? Is that 15? Did I do that right? Okay. All right. So here's the reason for that. Okay, so we have a modular ratio of 15. Okay, let me explain how we're going to utilize that. All right, and I'm just going to have sort of a conceptual image here down below, and we'll formally compute this out here in a second. All right, so here's our beam, right? We have a wooden beam, and it has 2 steel plates on the top and bottom, okay? Sound good? What we are going to do is transform that into a beam of a single material, okay? Now, here's how that's going to work. So here's the neutral axis. Now, what I'm going to do is I'm going to transform this into a beam that is made solely of wood, okay? So how that's going to work is the wooden beam is going to stay the same. The wooden center beam is going to stay the same. But what am I going to do with those steel plates? Okay. Well, those steel plates, remind me, how big are they? 6 inches by a ½ inch. Okay. So it's a ½ inch thick and it's 6 inches wide. I propose that in order to transform those into an equivalent piece of wood, we need to develop a wooden plate that's 15 times bigger. Why 15 times? Because that's our modular ratio. So essentially what we need is a really, really big wooden plate right here and a really, really big wooden plate here that is 90 by 1/2. And the same thing on the bottom.
So you have to do both of them and not just like one, so that the total increase in the area of the steel is 15 times larger?
Yes, I'm not following like why.
So
Extend that a little bit.
I was thinking of it as the total area of the steel, but each piece has to increase by 15, not the total area, not the sum.
Yes, it's each piece, okay? Because here's the reason why. I want you to think about this in terms of sum of moments, okay? All right, let's say here's our neutral axis, right? Okay, so this plate generates some force, okay? So let's think about this from a sum of moments perspective. There's a force in this plate, and then there's a moment arm, a distance from the centroid of the whole thing to the centroid of that individual plate, okay? What I want to do is I want to replace this with a component made of wood that generates the same moment, Okay? Now the way it generates the same moment arm is we keep it the same thickness, because from here to here is the same distance from here to here. But how do we generate the same force? We increase the width 15 times. So if we do that up here, we got to do that down there. That's a good question. Everybody okay with that? Okay. And how did I get the 90? It's pretty simple. You know, I'll say note N times 6 inches is 15 times 6 inches, which is 90. So that's how I got the 90. Everybody okay with that? It's not too bad, right? Okay. If you're okay with that, then I have a couple other things that I want to compute, because ultimately what we need is a moment of inertia of this entire shape. Okay? Now first off, we've already got the moment of inertia of the center beam, right? We did, what is that? BH cubed over 12? Everybody see that? So let's write down some quantities over here before we do some calculations. Okay, so I'm going to call this the beam, and I'm going to call this the plates. All right? First off, for the beam, we already computed a moment of inertia, and it was what? 1440? Was that right? Inches to the fourth? Okay. Now, what is the area of that wooden beam? It's 120 square inches, because the beam is what, 10 inches wide, 12 inches tall? That's pretty simple, right? Okay. Now what about the plates? Okay, we haven't done the plates yet. Okay, the area is simple. Okay, that's 90 times 1/2, so that's 45 square inches. And what about the moment of inertia? Well, it's BH cubed over 12. Remember, that's the width times the height cubed. So the height's really tiny. It's only 1/2. So that is 90 times 1/2 cubed over 12. And what does that come out to be? .9375. Do I have a second on that? Anybody else? Okay, good. And that's inches to the fourth, right? Because we have inches and then inches cubed. Okay? Oh, I'm dropping my pen. Hold on. Everybody okay with this? Now, I have one other thing I want to compute, okay? And that's this. Everybody remember the parallel axis theorem, right? How do you determine the moment of inertia? You take the moment of inertia of each individual shape and you add what? A times I plus A d squared, okay? Now, what are those d distances? Remind me. It's the distance from the centroid of the whole thing to the centroid of each individual shape, right? Okay? So let's take the plates first, okay? Let's take the plates first. I would propose that that is where the centroid of the whole thing is, right? Okay? And here's the centroid of those plates. What is that distance? How far is it from here to there? Remember that this total height, this distance, is 12 inches. That's going to be 6.25 inches. Is everybody okay with that? That's not bad, right? Okay, what about for the beam? This is an interesting one. How far is it from the centroid of this rectangular beam to the centroid of the whole thing? It's 0, right? Because they're right on top of one another, okay? So this term here is 0. Is everybody okay with that? Okay. There's a reason why I wanted that indicated now, because when we calculate our moment of inertia, I wanted everybody to be okay with that. Sound good? Okay. All right. Does everybody have this? Everybody have this? Okay. Can I go ahead and move on to the next panel? All right. Okay. Now, let's see. Let's see if we can do this a little more accurately. Okay, this is our datum. That's our centroid. All right. So that distance is 6 inches. Let's see. This 90 by a half. You all probably don't have to redraw this because you have it on your sheet. I'm just doing this for my sake. This is 90 by a half. This dimension is 10 inches. That dimension is 12 inches. Okay? What I'm going to do is I'm going to compute a moment of inertia. So remember how we did this before? We had the A, the Y, the AY, the I naught, and so on and so forth. My table is going to be a little smaller, and the reason why is because I already know where the centroid is. It's right in the middle. Like the centroid of this composite shape is it's right here, okay? So I don't need to worry about trying to do sum of AY or sum of A computations in order to determine where that point is. So I've got the shape. I have I naught. I have A. I have D. And I have I plus AD squared. It's going to be pretty simple, okay? So let's start off with the wooden beam. So we'll call it the beam, the center part. If I remember correctly, the moment of inertia was 1440. The area was what, 120? But what was D? 0. So what is I plus AD squared? 1440. There we go. All right. Now what about the plates? Let's do each plate independently. Let's start off with the upper plate. Which, by the way, if you see me write like PL, that's just plate. That's just shorthand for plate. All right. So the moment of inertia, now that was something like 0.93, what was it? 9375. What is the area? 45. Okay, and what's the distance? 6.25. So somebody tell me what is from the center to, I plus AD squared, that's 6.25. So what is I plus AD squared for this? We'll say like 2 decimal places is probably more than enough. 1758.75. Do I have a second on that? Okay, all right. Now what about the lower plate? Well, everything entry-wise is going to be the same except for one thing, and our D value, I guess, if we're going from the center to the top plate, if that's positive 6.25, this is negative 6.25. However, that doesn't really matter because we're taking I plus AD squared, so whether you have positive D values or negative D values, it doesn't matter. You're still going to get 1758.75. So that's not going to cause an issue. Sound good? Now, if I sum this up, this column over here, what do I get? 0.5. Everybody okay with that? So here's what I propose. I propose that I'm going to call this a transformed moment of inertia is 4957.5 inches to the fourth. Everybody okay with that? Now, what I want you to do is I want you to compare this against 1440. Remember, 1440 was the moment of inertia of the beam by itself. And the 4957, that's the moment of inertia of the beam with those steel plates. So you can see that those steel plates served to bump up that moment of inertia quite a bit. And if it's bumping up the moment of inertia, it's going to ultimately increase its stiffness and its response to bending. Okay? Everybody okay with that? So far, so good? Okay. Now, okay. What we're going to do then is this. Okay? I'm going to perform a bending capacity calculation on each material. Okay? And I'm going to do that in order to determine the maximum moment that this beam can withstand. Okay? And I'm going to show you how this is going to work. We're going to start off with the steel. Okay? We're going to start off with the steel. Okay. Now, our moment of inertia is 4957.5 inches to the fourth. Okay? Now, what was our allowable bending stress for the steel? Anybody remember that? 18, well, we can say PSI. We can also leave it as 18 KSI. That's fine, right? Okay. What was our moment of inertia? Or no, sorry, not our moment of inertia. Our modular ratio. I'm sorry. What was our modular ratio? 15. Okay. Now, let's also look at our C distance. Okay. All right. Our C is our extreme fiber distance. Okay. Let me explain what I'm going to do. I want to ask the following question: how far is it from the centroid to the very, 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 very top of the plate? How far is it from here to the very, very top of the plate? 6.5 inches. Everybody okay with that? All right. Sound good? Okay. Here's what's going on. Sigma equals MC over I, right? Okay. Sigma equals MC over I, but we need to adjust that by a modular ratio. Okay. Why do we need to adjust that by a modular ratio? Because our moment of inertia, let's go back to our transformed section, okay? Our transformed section, okay, is a section that has been transformed into wood, right? It's a beam that is only wood. We're doing a check right now on the stresses in the steel. So we have to multiply those stresses by 15 to sort of bring it back to evaluating a steel plate. So I propose then that, what do? We take sigma divided by N times I divided by C, and that's our moment, right? So therefore, our bending moment is, here, let me sort of rewrite it like this. It's sigma allowable times I divided by N times C. So that is 18 KSI, 4957.5 inches to the fourth. We have 15, 6.5 inches. What does that come out to be? $915.23. Do I have a second on that? Okay. Now, what are the units for that? Inch kips. Now, how do I convert that to foot kips? There you go. Just look at the inches and feet. Think about it like this. If I have 915 inches, how many feet is that? You just divide by 12. So what is that? .27 foot kips. Okay. Everybody okay with this? So basically, here's what we did, okay? Now that we have a moment of inertia, we use sigma equals my over I to determine what's the maximum moment on the steel, okay? Now here's the thing, all right? We had to incorporate our end value because we were checking steel. Remember, our original beam, or our transform beam, is made out of wood, okay? But since this is steel, we have to bring that modular ratio back into the mix. So here's what I'm getting at. All right. Now what I want to do is I want to check the wood. Okay? And so let's see how that's going to work. Our moment of inertia is still the same. It's still 4957.5 inches to the fourth. Now remind me, what is sigma allowable for the wood? 1 KSI. Okay? Now let's look at C. Okay? All right? Let me pull up my slide because I think it's going to be a little easier to see. Remember, here's the beam, okay? So before I asked you how far is it from the centroid to the very, 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 very top of the beam or the very, very bottom, and you said 6.5 inches. Now I'm asking you how far is it from the center of the beam to the very, very top of the wood or the very, very bottom of the wood, and what is that? 6 inches. Is everybody okay with that? All right. And I think you're going to see where this is going real quick. Okay? So this is 6 inches. Since we are evaluating in this step, since we are evaluating the capacity of the wood, we don't need to throw that modular ratio in like we did up here. All we have to do is say sigma equals MC over I. Because remember, the bending stress formula only works if you're considering one material. Well, in this design check, we are evaluating wood. And our moment of inertia is a moment of inertia of a section made of wood. So we don't need to consider the end. Does that make sense? Everybody okay with that? All right, so therefore, there we go. So therefore, our moment is sigma allowable times I over C, which is 1 KSI times 4957.5 inches to the fourth divided by 6 inches, not 6.5. And what does that come out to be? Say it again. 826.25, and what are the units on that? Inch kips. So from a moment standpoint, converting that to moments, we take that and divide it by 12. So what do we get that in terms of bending moment? 68.85 foot kips. So far, so good? Yes? Great question. Okay, remember, this moment of inertia that we use, this 4957.5, that's the moment of inertia of this shape up here, okay? And what is that shape made out of? Nothing but wood, okay? Because remember what we did, okay? We had a wood beam, right, with some steel plates on it, right? And we then said, well, we're going to turn that into a wooden beam with just wood plates on it. Okay? So the reason that we didn't incorporate wood into this design, or the reason that we didn't incorporate our modular ratio into this design check here is because we were checking the capacity of the wood. You know, we were using a moment of inertia related to wood, an allowable bending stress related to wood. Okay? Up here, we were using the moment of inertia of a wooden section, but we were checking the stresses in the steel plate. So we had to bring that modular ratio back into the mix so that we were comparing apples to apples. Okay? That's a good question. Does that make sense? Okay. Here's another thing that's worth mentioning. If we had instead done this, if we had said, okay, let's keep the steel plates as they are and convert this into a really, really thin steel plate so that we had just a steel section, what would have happened is this. We would not have used N here at all. Here, we, instead of dividing by N, see how we divided by N? We would not have included N here, and we would have multiplied by N here. Okay? Is everybody okay with that? The reason why we're dividing is because we turned everything into the weaker material. If we had turned everything into the stronger material, it would have been vice versa. Okay? Does that make sense? All right, everybody else okay with that? This is good stuff. This is good stuff. Okay. Now, let's talk about the actual capacity of this section. Okay? Let me ask you, this composite section, what is its maximum allowable bending moment? Is it the 68 or the 76? Think about it like this, okay? Here's my beam, right? Okay? Let's say I put 50 foot kips of moment. Is it safe? Well, I would say it's yes, because we haven't exceeded this value and we haven't exceeded this value. Now let's put 60 foot kips of moment. Is it safe? Yeah. We haven't exceeded that. We haven't exceeded that. What about 70? What if we put 70 foot kips of moment? Is that safe? No, it's not. Because while the steel plates are doing just fine, we failed the wood. Okay? So what is the maximum capacity of this section? It's the 68. Okay? Another way of thinking about it, and this is a term that you might hear in the engineering vernacular, is that for this composite beam, the wood governs its capacity. In other words, the wood has the most stringent requirements. The wood can only withstand 68 foot kips of moment, whereas the steel can withstand 76 foot kips of moment. So it's the wood that's sort of driving our design decisions. Okay? In other words, think about it like this. Let's say that I needed this section to withstand 70 foot kips. Well, as the designer, I probably wouldn't do a thing to the steel plates, but I'd probably be paying attention to the wood. Okay? What I might do to the wood is maybe I'll take the beam and make it wider. Or maybe I'll use a different species of wood that has a larger allowable bending stress or something like that. Does that make sense? So that's what I mean, and that's what we as engineers mean when we say that the wood governs the design. Okay? Is everybody okay with that? For you civils who decide to take steel design, one of the things that we'll talk about in there is we'll look at different types of connection scenarios. So we'll look at like bolted connections and welded connections and things like that. And for these connections, we'll have a variety of different design checks that we'll perform. Like how much load can it withstand under this state and how much load can it withstand under this state. And what you'll find is that one of those is governing the design and the rest are fine. And that's, I would argue, probably going to be the case in a lot of machine element design or steel design or any of these types of engineering computations and whatnot. Does that make sense? All right. Are there any questions about this example? This is a pretty intense example, and if you understand this, I think by understanding this example, there's a lot of background material about moments of inertia and about strong axis versus weak axis and the bending stress formula that go into this. Everybody okay with that? Any questions? Good. All right. Okay. if you're okay with that, I have one other thing in bending moments to talk about, and that's non-symmetrical bending. So let me pull something up real quick. This is example 23. Here. We're not going to do this example in class. Honestly, I don't think that non-symmetrical bending is that super important. I'm not saying it's not important. I'm just saying that I don't think that we really need to waste a lot of time in class talking about non-symmetric bending, and you're going to see why here in a second. Right now, I want to look at this. We derived our formula for normal stress as follows. Okay, so sigma equals P over A plus My over I. And hopefully by now, everybody is okay with that, right? And for now, we've neglected shear because it only causes shear stress, okay? This is two-dimensional, okay? What about in 3 dimensions, okay? In 3 dimensions, remember, we have 6 unknown components of force or moment inside a section that we would need to deal with. We have the unknown axial load, the unknown torsion, the unknown shears across both axes, and the unknown moments across both axes, okay? Right now, I'm going to neglect the shears and the torsion because those generate shear stress, and I only want to look at the axial forces and the moments because they generate normal stress. Now, don't worry. This is movie time. You don't have to, like, take super major notes on this because I'm not going to make you do this. I promise. This is not going to be, I don't think this is on a homework assignment, and I don't think I'm doing this on an exam either. I wouldn't really worry about it because you're going to see it's just kind of boring. What I want to do is I want to extend my derivation of bending stresses a little bit. If you remember, when we looked at bending stresses before, we looked at the equation of a line, just y equals mx plus b. Well, in 3 dimensions, if I'm considering an axial load, this bending moment, and that bending moment, we have to consider not the equation of a line, but the equation of a plane, okay? So we have 3 unknown constants we have to solve for. Now, I'm not expecting you to, be able to spit this out verbatim, but there's going to be a lot of things that should seem somewhat familiar, like, the area, what the definition of the centroid is, what the definition of the moments of inertia are. We're going to see another term pop up in our computations, which is called a product of inertia. So, for instance, the moment of inertia about the x-axis is the integral of y squared, and the moment of inertia about the y-axis is the integral of x squared. If you take the integral of x times y with respect to the area, you get what's called a product of inertia. And the reason I'm showing you that is because really, when it comes to non-symmetrical bending, that's the one thing that you probably don't know how to compute. Everything else you're going to see is very, very plug and chug. And another thing, if you have a shape that has symmetry, in other words, like an I-beam that has symmetry about one of those axes, then the product of inertia is 0. So it doesn't even matter. This is going to be very similar to before. We have our differential element of area dA. We say, well, the force in that element is sigma dA. The moment about the x-axis, sigma y. The moment about the y-axis, sigma x. Integrate those, split them up into a series of integrals. We start canceling out the stuff that we can. Everything related to the centroid is 0. So this is 0, that's 0. This over here is 0. And what we get is basically what we got before. That first constant is P over A. And then we have a 2 equations, 2 unknowns situation. Okay? Do a bunch of algebra and a bunch of alphabet soup, and you solve for your unknown constants, and this is your expression for stress. Now, this expression looks super nasty, and I understand that. The reason why it looks super nasty is because of this product of inertia. If you ever have a situation where you have a symmetric section, that IXY goes to 0, and a lot of this nastiness goes away, because if IXY is 0, this becomes just My over I, and this becomes My over I, and it makes it a whole lot simpler. As for computing the product of inertia, it's really straightforward, and that's what I want to show you, is just how to compute the the moment of inertia. If you look at that formula, everything in that formula, while large, is stuff we know how to compute. A moment of inertia about the x-axis, the area, the moment of inertia about the y-axis, and so on and so forth. It's all pretty straightforward. The product of inertia is another rote property. One point worth mentioning is that because the distances aren't being squared when you use your parallel axis theorem, it's not I plus AD squared, it's I plus AD times one distance and D, D from one axis and D from another axis. That property can come out negative, and that's okay. All right. If your section exhibits symmetry about either axis, then IXY is 0, and your formula is really simple. Okay? I just want to show you what a product moment of inertia calculation looks like. I have a pretty straightforward shape. Don't worry, I'm not going to make you do this. We're not doing this in class. If you go to Blackboard, I have this uploaded, and this is the entirety of the calculations. So here's the shape. Excuse me, I'm sorry. Here's the shape. So I have a rectangle, shape 1, and shape 2 is a triangle. For shape number 1, I've got the area, the x bar, the y bar, the ix, the iy, and then the product of inertia is 0. And then for shape 2, I have the area, the centroids, the moments of inertia, and then the product of inertia. Again, that product of inertia can come out negative. Once you get those quantities, it's really pretty straightforward. We take the areas, and then we compute the centroids independently. So from the datum, these are the centroids with respect to the x-axis and the y-axis. So we can do sum of ax over sum of a to get the centroid of the whole thing. Then we take the product of inertia. We take the individual d distances. So that minus that minus that, and then that minus that, and that minus that. Plug and chug, and there you go. I mean, I just don't think that it's really worth our time to spend 30 minutes doing that. So it's there. I'm not going to make you worry about it on exams or anything. It's pretty straightforward. Honestly, I'll say this. This is probably going to be most applicable to maybe you mechanical engineers. If you've got like an airplane wing that has a really weird cross-section, if you cut a section through an airplane wing and look at it, it's not a rectangle. It's really weird. It's like curved and whatnot. And if that's the case, if you're doing something that complicated, you're probably going to break out some finite element analysis or something like that anyways, and you're just going to model it and have it spit out the stresses, so you aren't even going to worry about this stuff anyway. So that's why I just want to show you. It's worth checking out. Let's move on. Everybody okay with that? Don't worry. That's pretty much going to be our be-all, end-all discussion of that. Now, we do need to spend a little bit of time talking about shear stresses in beams. Okay? We know that beams will generate bending stress. If you take a beam and you bend it, right, the top is experiencing compression, the bottom is experiencing tension. We know that. But do beams generate shear stress? The answer is yes. Okay? I have a book in my hand. It's actually a fluid mechanics book, so in here that must be a little bit of blasphemy. That's a joke, not a very funny one. All right. Watch this. Okay? I take this book and I bend it. Okay? It's really easy to bend, but what's going on with the pages inside the book? If I bend it, the pages are sort of just sliding, right? They're sort of sliding across from one another, right? All right? That doesn't happen in a solid beam, okay? In other words, imagine if I took these pages and I superglued them all together. The beam would get a lot more rigid, right? And what's going on between those pages? That glue is sort of keeping the beam together. So that interface between those pages is seeing shear stress, right? And that's what I'm trying to determine in this derivation is what is that shear stress in a beam, okay? Now, for my derivation, I'm considering this beam. I have a simply supported beam with a point load right in the middle. The reason why is this. Okay, if you draw the shear diagram and the moment diagram, is everybody okay with what that looks like? You have a shear diagram. You're going to have reactions at the hinge and the roller, so it's going to go up, flat, go down, flat, and go back up, and then the moment diagram is going to be linear. Okay? I use this example for a very specific reason. This beam is an analytical example of a section with constant shear. The shear is constant within a given region. Okay, so it makes my derivation a little easier. But here's something that's kind of interesting from a behavior standpoint. I have constant shear. Do I have constant moment? No, the moment changes, right? And that's actually a pretty fundamental relationship worth mentioning, is that it's actually sort of impossible to have a section with constant shear and constant moment unless you have some really weird loading going on. So yeah. Everybody okay with this? All right. Now what I'm going to do is I'm going to cut myself out a slice, and I'm going to look at this slice. Now what I've got drawn on this slice is kind of important, because if you look from left to right, I have positive shears, like a shear going up, shear going down, and they're just shears, they're just V. But the moments, that's not the case. I have moment on one end, but on the other end, I have M plus dm, some incremental change in moment. There's a reason why I am expressing a change in moment, but not a change in shear. And this is why. The shear is constant, the moment is not. Okay, so the moment changes. All right. Now, first off, these are probably the best images I've ever drawn on a PowerPoint slide in my career. So this took some time. So for such a simple formula. All right. So here's the thing. If the bending moment changes from one end of that section cut to another, so I'm taking that little individual slice, if that and we're going to investigate that slice. If the bending moment changes, I propose that the bending stress profile changes as well. So here's that little slice of that beam. So I've cut that slice out and I'm looking at it. Does everybody kind of understand what's going on these two images here to the left and right? I have, the centroid has zero stress, and as we go from the centroid, we get linear increase in stress. So on the left, I have sigma equals my over I. But on the right, it's not M, it's M plus some incremental change in moment, M plus dm, okay? Everybody okay with that? So the bending stress profile on the left is a little bit less than the bending stress profile on the right. There's more moment, okay? Is everybody okay with that? Now, here's the problem, okay? Even if the shear is constant, we know that there's going to be different moments on each side. Because if shear is constant, the derivative of moment is shear, so the moment's going to change. Okay, so there's that. Here's another thing. I don't care if the moment changes on one side to another. Equilibrium still has to be maintained. Sum of forces in the x direction still has to be zero. Okay, otherwise the beam is running away from us. Okay, so yes, there is a different amount of bending moment from one side of that section to another, but it doesn't mean that the sum of forces in the x direction doesn't equal zero. We have to generate some amount of stress to counteract that. And where do we get that? We get that from the shear stress. Okay? So here's what I got going on. All right? We're going to determine the total forces in bending. We need to integrate across the depth of the section. Okay? So I'm going to cut a little bit of a slice off the top of that beam. So here's my little element, and I'm going to cut myself a little slice off. Now, everybody agree that that little shaded area is however wide the beam is times however thick that slice is. Everybody okay with that? If you're okay with that, how do I determine the force on the left and the force on the right? Well, I say, all right, stress times that area will give me a force on that element. If I integrate across the height and across the height, I will get the force on the left side and the right side. Sound good? If that's the case, I sum forces in the x direction, some forces on the left, some forces on the right. Do a little bit of substitution. I know it's getting a little messy. Don't worry, I'm not going to make you write all this out because I know it's a little hairy. But all I'm doing here is I'm making some substitutions. Anytime I see a dA, I'm replacing it with b dy. Anytime I see a sigma, replace that with my over I. And anytime I see a sigma plus d sigma, replace it with that. Simplify it out, do a little bit of rearranging, and I get the force on the left, force on the right. Now, if I sum those forces up, okay, if I say that the sum of forces on the left and the sum of forces on the right, If I sum them up, I don't get 0. Okay? The sum of forces in the x direction doesn't equal 0 if that's the only thing going on, just a force on the left and a force on the right. What I'm saying is that that isn't the only thing going on. I'm saying that there is additional force in that section that's maintaining equilibrium. Where are we getting that force? We're getting it here. Okay? It goes back to the book. All right? If I take the book and I bend the book, the pages are sliding across one another. I propose that inside of a beam, inside these layers between the beam, that there's a force being developed that's keeping that beam flat. In other words, again, imagine what happens if I superglued all these pages together. That superglue is going to experience some stress if I bend the page, right? That's what I'm going to try and compute. I propose that where we're getting our equilibrium is that force generated from that shear. There's some shear stress developed between those pages, if you will, between those layers. What is the area of that sort of plane right here? Well, it's B dx. That plane is seeing some amount of shear stress, some tau. Let's see what that is. So I have the sum of forces in the x direction. I have the force on the left side, the force on the right side. This is the result of me simplifying that out through a bit of algebra. This is the force generated from shear. I want to determine what that shear stress is so that the sum of forces in the x direction equals 0. And how do I do that? It's just a little bit of rearranging. Okay? So I take that expression, put everything all over to one side, solve for tau, and here's what I get. Okay? Now I know I threw a lot of algebra at you and a lot of alphabet soup, but is everybody okay with that so far? Okay. Let's take a look at that box. Okay, I got a pile of junk times a pile of junk times an integral. Okay, let's take a look at that first pile of junk. What is dm over dx? Say it again. That's the shear, right? That's the shear. I, that's just the moment of inertia. B, that's just the beam width. This right here, this is a new section property. Okay. What we're going to call that is a first moment of area. We're going to call that term Q. Okay? It might seem super complicated because it's like an integral and there's, oh God, integrals. It's really not bad. It's actually really simple to compute Q, and I'll show you how that's done. But basically, we can take that expression and we can simplify it really quickly by recognizing that the derivative of moment with respect to x is shear, and that this term in the brackets is a section property called Q. And there you go. Our fundamental stress formula, our fourth and final fundamental stress formula, is the stress formula for transverse shear. And it's a function of four things: the moment of inertia, the width of the beam, the shear, and the first moment of area. And there is our fourth and final fundamental stress formula. If there's anything to write down, this is what's worth writing down. I'll give you a second because this is actually kind of valuable. Now, a couple things worth noting about this section. Okay, in general, when we write that expression, the V value is constant. The V value comes from our shear diagram. So if I samurai sword or lightsaber through a beam at a particular point, that's the shear at that point. That's typically a constant value. The I value, the moment of inertia, is also constant because you're cutting a section at a particular point. That point is going to have a moment of inertia. That's the section. Okay. Now, on a given section, the Q and the B value can be variable as well. Okay? Let me show you what's going on with that. This is a sort of a conceptual plot that's showing what's happening with bending stresses and shear stresses when you look at given beams. Let's look up top. Okay? Up top is looking at a rectangular section. So the first profile is the bending stress profile. So this is sigma equals my over I. And I think that everybody is okay with that. So sigma equals my over I, linear from the centroid. This is the shear stress profile, okay? So I propose that if your beam is rectangular, so let's say I've got this book and it's a rectangular beam, and I bend this book, that the worst case shear stresses are in the middle of the beam, okay? That's actually completely different than the bending stress. The bending stress is 0 in the center, but the shear stress is maximum at the center. And if you look at the top and bottom has your worst case bending stress, but it doesn't have hardly any shear stress. Okay, so it's sort of inverses of one another. Now, for I-beams have something that's kind of interesting. Okay, watch this. Remember, it's VQ over IB. B is the width of the beam, and that can be variable. Watch this. As you start at the bottom and work your way up, watch it. Here's B, here's B, here's B, bam, here's B. B has a sudden change, right? And so think about what happens. Your B suddenly goes from here to here, it gets smaller, right? So if B gets smaller, VQ over IB gets bigger, right? So if you look at an I-beam, you have a sudden jump in shear stress right there at that flange-web transition. See, in civil engineering, a very common vernacular when you're thinking about I-beams is that the flanges carry the moment and the web carries the shear. Here's why. Because the web, at that point where the flange and web meet, you have a sudden jump in shear stress. The flanges hardly see any shear stress at all, okay? And as for bending, well, where do you get most of your moment of inertia from a beam? You get it from having flanges as far away from the centroid as you can. So that's where you get a lot of your bending stress and your bending capacity. Everybody okay with this? Any questions? It's in bad, right? Okay. Let's see, what time is it? Well, I think we can get some stuff done on this problem. Okay. Now, I have a beam here that's being subjected to a 6,000-pound load over here off to the side. I want to determine the maximum shear stress and the shear at a given section, okay? Now, the cross-section of the beam is 2 inches wide and it's 4 inches tall, okay? So what we're going to do is we're going to take this problem one step at a time, and I think you're going to see this is really, really simple, okay? Like, bending stress has a lot of complication. You can have composite sections and things like that. Shear stresses, it's usually a little more straightforward. All right, so all right. Here's our beam. Hold on. Okay. Okay, so here is our beam, okay? Now, one of the things I did not give you on this example are the support reactions, but would it be all right if I just told you that this support reaction over here is 2,000 pounds, and this reaction over here is 4,000 pounds? Would that be okay? Or do we need to go through that? I mean, we can. I think if you sum moments, here, we have 6,000 times 4. We have to have so much times 6, so that's 4,000, so on and so forth. Okay. Oh, wrong one. I was like, why is that not showing up? Okay. Everybody okay with this? Now, let's draw the shear diagram. excuse me. So what does the shear diagram look like? We start at 0, we end at 0. So start at 0, then what do? There we go. Then no change, no change. This is 2,000. Then what? Down to negative 4,000. Then back up to 0, right? So I propose then that a maximum shear on this section is 4,000 pounds. And again, when it comes to shear, whether or not that's a positive shear or negative shear doesn't really matter. It's still the same force effect being applied to the beam. So it doesn't really matter. Okay? Now, for our cross section, we have a beam that is 2 inches wide, and that height is 4 inches. Now, one thing I will mention is that the beam has a height of 2 inches, or the beam has a width of 2 inches that is also constant. So that makes our shear stress computation pretty easy. All right. Sound good? All right. Now, we're going to need the moment of inertia. So that's BH cubed over 12. So 2 inches, 4 inches cubed over 12. What is that? Say it again. 10.6. Like 10.67 inches to the fourth, right? So far, so good? Okay. Now, let's take a look at this first moment, Q. Okay. Let's revise or reread this definition a little bit, because I think this definition in this integral probably makes it a little more complicated than it seems. Okay? Q is defined as the first moment of area above which our shear stress is being evaluated. Now, when you plot shear stress, this is what it looks like. Okay? So for a rectangular section, where is the maximum shear stress? Dead center. Okay? So if you want to know how to determine Q, it's real simple. All right? Here's what we've got. I'm going to say in general. All right? Here is our neutral axis. Let's say that we're trying to determine the stress right there at that red line. Then what we do is we say that area times that moment arm, Q equals AY. That is Q. It's a first moment of area. That area times that distance. So that's in general how you would compute Q, because you're just integrating that area times the moment arm. That's it. Okay? So for tau max, here's our centroid. Maximum shear stress is right here, right? So what we need is that area. So that area is what? BH over 2, right? And then the moment arm H over what? 4. So therefore, BH squared over 8. What does that come out to be? Say it again. 4. So here, let me move this up a bit. So our tau max, VQ over IB. So we've got 4,000 pounds. Q is 4 cubic inches. I is 10.67 inches to the 4th. B is 2 inches. What is tau max? First off, what are the units? It's a stress, so. PSI. There we go. What are we getting for a value? $749.77. If you track the decimals there on the bottom, I bet you it comes out to an even 750. That's it. That's exactly it. Now, how do we do the, so here's the second part. That's the maximum shear stress across the beam overall. How do we determine the stress at this section, 1 inches from the top of the beam? Well, what was the shear on this section? 2,000 pounds. And how do we determine the shear stress at a point 1 inch from the top of the beam? Well, here's the beam. That area, 1 inches from the top, just determine another Q. So let's just do that real quick. Has everybody got this? So part B, our V in this case is 2,000 pounds. Our moment of inertia is still 10.67 inches to the 4th. Our B is still 2 inches. And as for Q, here's the beam. How tall is the beam again? That's 4 inches. So this is 2 inches. And what was it asking for? The shear stress at a point 1 inch from the top. So really they're wanting the shear stress right there. Okay? So help me out first off. What is that moment arm going to be? We get 1.5 inches, right? 1.5, so that's 1.5 inches. And what's that area? Well, hold on. This is 2. And that dimension is 1. 2 inches. So therefore, all right. So there you go. Tau equals VQ over IB. Oh, exactly right. Cute. Cute. Well, what do we get here? Excited for dynamics, that's what it is. I love this job. Anybody get a value here? Point like 25, something like that? 0.16. How about this? 0.2. And then that's PSI. All right. Is everybody okay with this? Any questions? That's exam 2. Everything, so everything from exam 1, the axial loads and torsion, up until right now, that's exam 2. So I'm not going to, it's not a comprehensive exam, so I'm not going to ask you about torsion and axial loads and stuff like that on the second exam. But the second exam is going to have all the section properties, bending stresses, shear stresses. That's the second exam. Homework's number 4, homework's number 5, and then I believe, what is it, like example, what was it, 17? Is that when we first, I don't remember, but like whenever we first started doing section properties all the way to this. Sound good? All right. That is all I have got for you all. I will see you all next week. You all have a fantastic weekend.